So for this example, we are going to be using a complete weighted graph again to determine the most efficient route or circuit, except rather than using the brute force method to determine this, we're going to be using the nearest neighbor algorithm. And an algorithm is simply a set of established steps that are to be taken. So here it says, a traveling nurse drives from her home in Ashland to visit patients in the cities of Burlington, Carson, Darien, and Easton. She returns home after her last visit. The following table lists the distances in miles between each city, and you can see here's the table here. Using the nearest neighbor algorithm, determine the shortest route she would take. So obviously the nurse is looking to determine the shortest route. Except we're not going to use the brute force method, because the brute force method means you have to determine every single possible circuit that's within a completed graph. Here we're not going to do that. We're going to use the nearest neighbor algorithm. Now, of course, the first thing we have to do is we're going to represent this scenario using a graph. So we have Ashland, Burlington, Carson, Darien, and Easton. So we have 5 cities. So I'm going to have 5 vertices that are going to represent those cities. And since I have 5, I like to keep my graphs as geometric as simple as possible. So I'm going to use a pentagon, which has 5 vertices, to start off my graph. And I can label this one Ashland, Burlington, Carson, Darien, and Easton. Now, to make it a complete graph in which every vertex is attached to every other vertex, just start at one of the vertices and connect it to every other possible vertex. So how about if we just go like this? There to there, over to there, here, and there. And we'll just kind of do that for each vertex. I'll go to here, here, and then all the way up here. And we just kind of work our way around. And then finally, we'll close it off here. So that's our complete graph that would represent this scenario. Now we're going to put in the weights. And if you recall from the earlier example, the weights were money. They were airfares. Here they're distances. So from Ashland to Burlington, that's 6 miles. So I'm just going to put in 6 right here. Ashland to Carson, that's 8 miles. So I'm going to list it right in here. That's this edge right here. Ashland to Darien, that's this edge right here. So I'll put it in right here. And then Ashland to Easton, that's this right here. That's 7 miles. Burlington to Ashland, that's 6 miles. I already have it. Burlington to Carson, that's 11 miles. Burlington to Darien, that's this one here. That's 10 miles. I'll put it in right here. And then Burlington to Easton, that's also 10 miles. So I'm going to put it in right here. Then we go from Carson up to Ashland, that's covered. Up to Burlington, that's covered. Carson to Darien. Carson to Darien, that's 4 miles. And then Carson up to Easton, that's 13 miles. I'll put it in right here. Darien to Ashland is covered. Up to Burlington here. Carson here. So then Darien to Easton. Here it is right here. That's 15 miles. And I think we got them all. So here is our complete weighted graph that represents this scenario. Now, if we were to use the brute force method, since there are 5 vertices, then there are n minus 1 factorial possible circuits. So that would then be 5 minus 1 factorial. That's 4 factorial. That's equal to 4 times 3 times 2 times 1. That would be 24 different circuits that we would have to go ahead and list. And that is doable. That's 24, but it seems to be a lot. Certainly if it was 6 vertices, that's 6 minus 1, that's 5. That's 5 times 4 times 3 times 2 times 1, that's 120. So it seems very impractical to do that. So the nearest neighbor algorithm shortens that very easily. So the algorithm says, step 1, start where you want to take off from. So she lives in Ashland, and we're going to go to the nearest neighbor, or we're going to go to the vertex that's connected with the edge with the smallest weight. So we're starting at Ashland, going over to Burlington, that's 6, going down to Carson, that's 8. If we go down to Darien, that's 12, and if we go to Easton, that's 7. So the smallest would be going from Ashland to Burlington. And then we repeat that until our circuit is complete. So if I went from Burlington to Carson, that's 11 miles. Burlington to Darien, that's 10 miles. That's this one here. And Burlington over to Easton, that's also 10 miles. So if you come across where you have weights that are the same, just pick one. It doesn't really matter which one, just kind of randomly pick one. How about if we go from Burlington over to Easton? And we keep doing that. Easton, I'm not going to go up this way because then that ends my circuit. I still have Darien or Carson to visit. So if I go down to Carson, that's 13 miles. If I go down to Darien, that's 15 miles. So I'm going to go down to Carson right here. That's closer in distance than it would be to Darien. Then from Carson, the shortest one would be to Darien right here, 4 miles. Now we've got all the vertices accounted for. We then go from Darien back home up to Ashland. That's 12 miles. So then we just go ahead and we add up those distances. Here's Ashland to Burlington, that's 6. Burlington over to Easton, that's 10. Easton down to Carson, that's 13. Carson over to Darien, that's 4. And then back home from Darien up to Ashland, that's 12. We then go ahead and tally this up. That comes out to be 45 miles. However, the drawback of using the nearest neighbor algorithm is it's not going to guarantee the shortest route. Using the brute force method, since you're covering every single solitary route, you could just see which one is the shortest one. But using the nearest neighbor algorithm, that doesn't necessarily guarantee the shortest one. But it's pretty close. It's a good approximation, but it's not going to guarantee the shortest one. So what we could do is, since this is a circuit, in other words, we're always going to end up where we started, or every single solitary vertex is going to be covered anyways. So even though the nearest neighbor algorithm says start at your starting point, which is Ashland for the nurse, in actuality, the nurse would have to start here. However, in order to be able to determine the shortest route, is we don't have to necessarily start there as we tally them up. So we could start at any vertex. So maybe that's what we should try. Let's try at any vertex. And when we do that, that's known as the repetitive. I'm going to write it down up here. Repetitive means repeat. We just keep repeating the nearest neighbor algorithm until we come up with the shortest one. And how many times do we have to do that? Well, since there are 5 vertices, we're just going to do this 4 more times and see which one's the shortest one. So rather than starting at vertex A, we'll start at B. use the same idea. We'll go to the shortest or the nearest neighbor, and that would be up to A. That's 6 right here. So we'll go from B to A. Then from there, we'll go to the next shortest one. Well, here's 7. So we'll go from A to E. Go to the next shortest one. We won't go across to B here to 10 because that will close off our circuit. I want to make sure I get to the other 2 vertices. So if we go down to C, that's 13. If we go down to D, that's 15. So we'll go down to C. From C, finally back over to D. And then from D, back up to B. And of course, we go ahead and we add up those distances, those weights. B to A, that's 6. A to E, that's 7. E to C, that's 13. C to D, that's 4. And then D back to B, that's 10. We go ahead and we tally all these up. And there's 40 miles. So we shaved off 5 miles. So it's going from B to A to E to C to D back to B. Well, that's the same as going A to E to C to D to B back to A. So we can start to determine the shortest route from any vertex, but then eventually she would start at her vertex using that route. So let's try C. C right away, the shortest one, C to D. C to D. Then D up to B. That's 10. Then from B to A, that's 6. A down to E. And then E back down to C. Add them up, that's 4 plus 10 plus 6 plus 7 plus 13. That also tallies up to 40. So far, rather than having to start at A to determine the shortest route, I just switch from B or switch to C, and already I found shorter routes. Let's try starting at D. D obviously will go over to C. C, we could either go up to B, go up to A. A is shorter. A to B. B over to E. And then ending back at D. So add it up, D to C, that's 4. C to A, that's 8. A to B, that's 6. Then 10. And then 15. Add this up, that's 43 miles. Longer than the other 2, but still shorter than the original one, in which the nearest neighbor algorithm says you have to start at A. Well, you don't. Using the repetitive nearest neighbor, you can start at any one. Now, the difference between this and the brute force method is this. You only have to start at each vertex. If there's 5 vertices, as there is here, you're only going to have 5 possible routes. Using the brute force method, there are 24 possible routes. So we'll finish off with E. If we started at E, E up to A to B, B down to D, D to C, and then C to E. That gives us 7 plus 6 plus 10, then 4, and then 13. Tally it all up, and this also comes out to be 40. So any one of these shorter routes here would work. If we use strictly the nearest neighbor algorithm, where it tells us to start specifically at Ashland, we're going to come up with 45 miles. But if we use the repetitive nearest neighbor algorithm, which we pick or use every single one and see which one's the shortest, well, we can have either starting at vertex B, vertex C, or vertex E. Then there you go.